final day of our great pleasure to welcome Rudolf Triebel. Rudolf did his PhD in Freiburg and afterwards spent significant time at ETH Zurich and currently he's a group leader at DLR, which is the Deutsche Luft- und Raumfahrt, so the German NASA, and leads the group on perception and cognition. And at the same time, we're very lucky at KIT to have him as a professor for intelligent robot perception, right? Okay, that's great. And today he'll teach us about XAI and robot perception. So let's welcome him.
Thank you. Thank you for the invitation. It's a pleasure for me to be here. And yeah, today I'd like to show you a couple of things that are for my own lecture that I'm also teaching here at KIT. And I'd like try to organize it a little bit in the context of explainable AI, but the major topic will be on uncertainty and how we can use uncertainty to find errors in machine learning methods and so on. So that's kind of the first step to get to an explainable system. The motivation I'd like to start with is, let's say you have a robot, right? As we always have in mind, we always want to use them for something useful. For example, they should bring you some objects, right? You have, I don't know, a banana here on this table, and you say to the robot, please bring me that banana, right? And then, of course, there's a lot of things that the robot has to do before it can do that. The first most important thing is always perception, right? It has to see the environment, it has to detect these objects, it has to know how it is positioned with respect to its own camera, and then it also needs to know how to place the fingers and so on, right? So these are the at least first couple of steps that the perception part has to solve before you can do any action, right? Of course, then the action step is also important, and of course we have to plan a path. We have to find a smooth trajectory which is collision-free and so on. But first of all, and this is the topic of this lecture here, we're dealing only with perception, right? How do we find this object, and how can we also place our fingers? Now, the first question is, why is this difficult, right? There's, of course, many different ways of doing that, but there's at least two major problems with this setting. And the first one is it's a so-called inverse problem, right? Inverse problems are called like that because usually what we have to do is we have to find a plausible cause for a given effect, right? And this is the example of this image here, right? So you have a projection of some 3D world into a 2D world, but what we also only observe the 2D world, right? We never have the 3D representation of this, right? And this is a general thing in computer vision, right? In general, we have only this like projection of the world, but how what's the cause of that is hard to find, right? So in this case, you see the kind of bunny which hops in front of the projector, and it looks like a hand. And if we look at this image, it would feel like this is a hand, but in fact, it's actually something else, right? And this is a question that we have very often, right? We see something which might look like some known object, but in the end, it's something different. And this is one major problem in general in computer vision and also in robotics. For example, object detection and grasp detection are also similar things, right? So finding the right grasp for a given object is a similar problem like this one here. And one way of addressing that is by machine learning, right? If we see this object very often and you train your model with bunnies, right? Then you would at some point be able to infer that and say, I've seen this scene very often, and I know that there's a different possible cause for the same effect, and then I can reason on that cause when I have this effect. And the second problem we have is the so-called open world assumption, right? So here we have an example of where the robot knows 2 or 3 objects, right? But then there's another object it doesn't know, right? And important to know here is that you have to distinguish between the known and the unknown, right? So we not just saying this is something, whatever I know, right? And I try to match it to something known, but it's a next step to be able to distinguish something you haven't seen, right, from something that you have seen, right? And that is another big problem also, because we assume usually in robotics that wherever we are with the robots, there's always something that we haven't seen before, right? We cannot assume that the world is known, the world is closed, because that will then cause effects, will cause problems, right? So whenever there's something happens that is unexpected, then the robot would not be able to react on that. So these are the 2 problems that we have to solve. And and we are doing this, what I said already, this is machine learning, and this is we address this with uncertainty, right? So if I have a good uncertainty estimate about the objects, then I can use that same uncertainty estimation to tell whether something is unknown or not, right? If it's too uncertain, then I say, well, this is something I haven't seen before. So a small disclaimer before I go on. So this is a lecture on explainable AI. I'm not going too much into detail about the general topic of explainable AI. However, what I'm doing is I'm going to tell you something about introspection, right? Introspection means when does the robot know that it doesn't know, right? So when can I tell you this is something unknown or something known? And we use uncertainty to do that, right? This is our main tool to distinguish this the known things from the unknown things. And we use two kinds of different uncertainty methods, the model and state uncertainty. And our aim is to relate uncertainty predictions with wrong predictions, right? We want to be able to say if something is uncertain, then very likely it's a wrong prediction, right? We want to kind of mitigate the problem that very often machine learning methods give us a wrong prediction, but they are very certain about it. And this is what we call overconfidence, right? They tell us a wrong prediction, but if you ask it, how certain are you about it, then it says, yes, I know this is the one thing. And in fact, it's not true, right? So if we have a better way of relating unknown or wrong predictions with uncertain predictions, then we can mitigate that problem. This will help us to find detection errors, right? So this is the first step in explainable AI. So first of all, if you want to detect the error, it's the first thing. Then, of course, the second thing would be to determine where the error comes from, right? And the last thing is, of course, to mitigate the error. In this lecture, we're only covering the first part of this, right? This is only detecting the error by finding uncertainties. So let's give me an example on that. This is a typical example of a scene from a car that drives in the city. You see a segmentation of the image that the car observes. And you can see all these objects that it detects, right? So this is the first thing. And the second thing is it also finds bounding boxes of relevant objects in the street. In this case, you see pedestrians or persons, and you see this bounding box that is around this object. But along with this is important, you don't only have a label, but you also have a probability. And this P here is the probability of telling how likely is it that this actually is a person, right? In this case, it's not that high. It's 64% that you have this probability. And this might mean that the method is not too certain about it, and that you might then find methods to mitigate that and see whether that's right or wrong, right? You can then find methods to say, do I need that? Do I use that information or do I not use it? There's two questions I'd like to cover now today for the couple of next slides here. This uncertainty that you get here, it has different kind of sources, right? Different kinds of reasons why you are uncertain. And I'd like to show you where they come from. And the second thing is, how can we compute it, right? How can we compute the uncertainty and then use it? So the first thing is these sources of uncertainty. And there's at least 2 or 3 of them, which I'd like to quickly show here with these images here. So imagine you have a data set like this one here, a simple data set X and Y, right? And as you see here already, every data set that you observe is noisy, right? There's always noise in the data. That means if you plot your data points like this one here, you will see always this kind of spreading out of the data points. Now, if you have a model that is behind that, then you might have this one here, which kind of explains the data perfectly, but it will never be perfectly connecting all the points because of this noise, right? And this is inherent in any data set, right? Any data set is noisy, and that's because of the data uncertainty. And this is an uncertainty that we cannot mitigate, right? This is something that we have to calibrate. We have to find ways of estimating that uncertainty, but we cannot reduce it, right? Because it comes from the camera, it comes from the data, it's there, right? The second kind of uncertainty is the model uncertainty. And this is the one that is shown here. And I usually like to explain from here to here with the expression of even if. So if you say, even if you had no data uncertainty, right? Even if this noise was not there, then in that case, you also have uncertainty, which comes from the model. Now, in this case, what you see here, the data points are now perfectly aligned, right, on the model. Like this blue one is the ground truth model that tells you where the data comes from or where it's sampled from. And we, in this case, assume that there's no noise in the data, right? That means they're all perfectly on the line. But still, if you now do some learning, right, some training step, then what happens is that you have different kind of models, right? And these are these red lines here. So you have one red line here and this other red line here. And this simply comes from the fact that the training process is random, right? There's some randomness in the training process. And whenever you train your model, then you will have different kinds of results, right? You have these different curves here. And this gives a problem because you cannot rely on the model that you've trained on, because it might be either this curve or this curve, and they both explain the data in the same way. They're both equally well useful to explain the training data. And then the question is which one to use, right? Regular models just use one of them and rely on this one. But intuitively, you also want to take into account the other one, right? And this is the point where the uncertainty comes from, right? So if you now use this red curve here for predictions, then you get other results than the other one. And because of that kind of because it's not clear which one to use, you introduce uncertainty, right? Because then you don't know exactly what's the result, because you can have different kind of models. And the same thing is here. This is again another even if. So even if you didn't have that problem, even if during the training data, and the training data is between here and here, right? You see this kind of bounds where the training data sits. Even if in that area of the training data you have a perfect model, then you still have the problem that models outside the training data, they disagree, right? You might have one model that goes here and the other one goes here. And so if you now take this as a prediction tool, right, and you want to predict outside the training data, right, which is this out of distribution thing, then you might have disagreeing models, right? These models tell you different things. And then again, you have this problem of uncertainty, right? So this is a different kind of uncertainty here. And this is all called for the regression case. Regression means we have x and y, where x and y are real numbers or vectors in real space. If you do the same for classification, then you have a similar situation, right? So classification, here, this is the data uncertainty where two classes just overlap. And this is always the case. You will never be able to mitigate that problem, but you have to cope with it. The second thing is here, if you have two classes that separate, or two models that separate the two classes, right, model 1 and model 2, then you have a low uncertainty between here, but then here you have a high model uncertainty because there's two different explanations of the data, right? So there's two possible reasons how to separate the two classes, and you never know which one to use, and that means you introduce uncertainty just by the training process. And this is the case of outer distribution, which is also known here, right? You have two classes, which is in the training data set, and this third class is the red one, which is away from the training data, right? And this also causes this uncertainty. So now the problem is, how can we compute, or how can we now, going back to this example here, how can we obtain predictions, right? How can we first find these labels here and then also find these uncertainties? And in principle, there's two ideas to do that. One is reasoning, and in particular, we're looking into Bayesian reasoning, and the other one is learning. So two kind of strategies to get up to this information. Now, Bayesian reasoning is different from classical logic-based reasoning. In logic-based reasoning, you have from A follows B and from B follows C, and then you can follow that from A follows C, right? This is the typical logical reasoning thing. In Bayesian reasoning, we don't have that. In Bayesian reasoning, we are looking into probabilities. And you can think of this as, for example, this case where you look out the window and you see the street is wet, right? And then there's different kind of causes for that effect. And you can never tell that that it's certainly the case that it has rained so that the street is wet. So there could be different causes for the same effect. That means someone else could have just watered the street. And so that means there's just a probability that it has rained, but it's not certain that you have done that, right? So this is this turning around between effects and causes, right? If you know, if you see an effect, you cannot clearly say which cause it was because there's different causes for the same effect. So what we do here is we formulate probabilities, and I'll show you very quickly how this works. I don't know how many of you have heard about Bayesian reasoning already. So yeah, maybe I'll give you a very quick primer on that, how this looks like. The main idea is to combine knowledge, which means the prior knowledge, with some observations, which we call the likelihood, and then we come up with the posterior, which again is a probability. And then we find model uncertainty by averaging. And we call this marginalization. And then deep learning is a different kind of approach, which most of you should have seen already beforehand. This is the idea of determining model parameters from training data, right? You collect a lot of training data and then find model parameters and then apply those to the test data. So let's very quickly go through that in a nutshell to show you how this works. This is a very simple idea of doing Bayesian reasoning. So suppose we have a robot like this one here. It has a simple sensor that measures light, and you want to reason whether the door is open or not, right? And you do this only based on the observation that you get from the sensor, right? The problem with that is, and that's the reason why we do this here, these sensors, they may fail, right? So the sensor is never perfect. It can measure light when the door is closed, and it can measure darkness when the door is open, right? Usually you say when the room inside is lit, right? Then very often, or in most of the cases, whenever the door is open, you will see some light. However, because the sensor is wrong, yeah, it can do the opposite, right? There are cases where, despite the fact that the door is closed, you will see some light, and even if the door is open, you will also sometimes find some darkness, right? Because of that, we have to deal with uncertainties. And what we do here is we do this kind of Bayesian reasoning, which is a conditional probability, right? So we have two random variables, Z and open. Z is the observation of light. In this case, it's just a binary variable that is either light on or light off. And open is another binary variable that's either open or closed. And our reasoning is the probability of the door is open, given that the sensor measures light. Right? So this bar here means conditioned on the fact that we observe some light here. Right? So if we say this is light, then what's the probability that the door is open? And we do this using Bayes' rule. This is the classical way of doing it. So we turn things around, right? We turn the cause and the effect around. Why is that? Well, because causal reasoning is sometimes easier, or usually easier, than diagnostic reasoning. Right? We want to have a diagnosis. We want to have an explanation of our observation. This is here, given that. But we do this by turning things around and say, hey, we have this likelihood, right? And this we can calibrate, right? We can obtain this probability more easily by opening the door and then measuring how often we get some light, right? So we just get a probability, let's say 80%, right? We count the cases where we see some light when we know that the door is open, and that's calibration of the sensor. We know then, for example, 80%, right? And then this is the probability that we get here. Then we have, of course, a prior. A prior information is something we can add into the system. We can say, for example, the chances that the door is open without any prior knowledge, without any other knowledge, is 50%, right? Simply by estimating how often doors are usually open or not, right? This is this prior of open. And then by multiplying those two, we get the posterior, which then gives us the diagnosis of the observation, right? We have an observation Z, and we find the diagnosis of that. And the interesting thing here is we can compute this with this one here. We just, the Bayes rule, what it does is it takes into account all the other possible causes that we might have, right? There's another cause not open and so on. And we multiply, or we sum them up here in the denominator. And by that, we get the probability of this posterior. So this is the rough idea of Bayes' rule. There's another idea in Bayes reasoning, which is called marginalization. And this is shown here in this example here. If you now take an action, right, if the robot has to, for example, do something with the door, and for example, in this case, it's the action of opening, then what you can do is you can describe it in this kind of transition diagram. You have two states, open and closed, and you have probabilities that go from one to the other one, right? So for example, if you're here and you close the door, I think the action is close the door, then in 90% of the cases, the door is actually closed, and only in 10% of the cases, you stay in the state of open. And why is that? Well, there might be failures, right? The robot might not grab the handle well, whatever. That means there might be a reason that you stay in the state open, right? Because you couldn't actually close it. However, if you're on a state closed, then you cannot open it by taking that action, right? So if the action is closing the door, then with 100% chance you stay in the state of closed. So this is just an example of how you can do this in a probabilistic way. And now we use the so-called marginalization step, where we take previous steps, right? This is time steps, right? This is like in the previous time step, and this is the current time step. So if in the previous step we have some kind of distribution where how the door was, then we can multiply that with the transition from one state to another one. This is the state transition here, which is the action U, previous time step, current time step, and we sum this up over all previous time steps, right? And this we call marginalization. And if we have a continuous state space, we just replace the sum by the integral, but other than that, it's the same. So this, in summary, means we have two kinds of updates. We have the sensor update and the action update. Sensor update applies base rule. Action update applies marginalization. And by the end, in the end, what we have is a so-called belief, which is nothing else than a distribution over all state spaces xt, given all actions and observations. Right? This is then what we get in the end by doing these two steps here: Bayesian rule and marginalization. So this is the idea of Bayesian reasoning. Right? We can use that, for example, to estimate whether doors open or not. The other kind of thing that we can apply, and that we apply a lot in robotics, is learning. And this looks a little bit simpler or different. Here, the idea is that we have many kinds of input sample or input features, right? We first multiply them with some weights W, and we sum them up, right? It's a very simple operation. We take all these phi's here, which are, for example, pixels, whatever input data. We multiply them with some weights, and then apply some sigmoid function here. In this case, this function here, to do some predictions on that, right? And we use this notation here. We have the training data X and Y. Y hat is the known output, right? And now we adjust the parameters W such that the output is close to the estimated output, right? We just turn these knobs here. We turn these weights here so that the output that we want to have is equal to the one that we get from the network. Now we can, of course, do this in multiple cases, right? Not just one, but in many of these outputs here. That means we have an output vector, not an output number. And of course, we can stick this together and have layers, right? So every layer does the same thing. And that means we kind of build up a very large model with many of these parameters W, right? And that's called deep learning, right? In the end, what we have is a network like this one here with many layers here. These might be convolutional layers and fully connected layers and so on. In the end, you can think of this as a big, large function with many parameters W here that we have to adjust, right? Such that the output that we get is the true output that we get from the training data. Now, if you have now these two concepts, reasoning and learning, we can think of what are the best things of two, and how can we combine them in the best way, because there are benefits and drawbacks for both. And the ideal thing would be to just combine the two, right? So Bayesian reasoning, for example, it's very nice because it has a probabilistic formulation, which we don't have in learning, not in general. And we have this implicit representation of uncertainty, right? We can represent uncertainty with probabilities. We have a joint reasoning from prior information and sensor informations. And it's very restrictive, right? It needs some specification of the model. We have to find by hand the likelihood and the prior. We have to define this manually. And this is a kind of an issue, right? It's not so easy very often how to do that, right? Of course, simple thing would be obviously use Gaussians, but then very often these don't work so well, right? So it's not that straightforward to actually do that. And this is where the problem comes here with reasoning, right? So can we mitigate that problem a little bit? It's also not scalable to large data sets, right? So this is another problem. So if you have many with thousands or millions of data points, then it's not so easy to do that. However, it gives very good uncertainty predictions, right? So if you want to have uncertainties, it will be good to use reasoning. If you want to do good label predictions, right? If you want to have a good predictor that gives us pedestrian or whatever, then we use learning. However, we have this other downside that we cannot get the uncertainty, right? It's a functional representation. We have parameter optimization for training data. In general, it's a simple model with many parameters that can express more general functions. However, it scales well, but and training can be done efficiently. However, we don't have this uncertainty. And now we want to kind of combine the two into a common framework. And the idea behind this is the following. First of all, if you look at how deep neural networks work, we can think of this as finding the best set of parameters, right? Either the best likelihood or the best posterior, and then use that parameters to actually do the inference. So if you go back to our image here in the beginning, what they do is they just find one of these red lines, right? This is this W star, which is just one of these red lines, and then use that model to do the inference, right? And you can think of this already, okay, this is probably not so nice because what happened to the other model that is also possible, right? So the main idea of Bayesian learning and Bayesian deep learning is to not take into account just one of these models, but also the other possible models, right? So there's a lot of other possible ways to explain this data, and you can also use those other models. So instead of having an inference function here like this one here, you will have an inference distribution, right? This P here is the so-called predictive distribution, which gives us the probability of a new sample Y star, given the training data X and Y, and the input sample X star, which is the new image, right? So you have training data, and then you have a new image, right? That shows you a scene, for example, from the car, and now you want to find a probability of seeing a pedestrian route. And now we use the same two concepts as we had before in Bayesian reasoning. We use marginalization in the inference step, and we use the Bayes rule in the training step, right? In the inference step, what we do is we have already, now this is of course backwards, right? We have already done the training, right? This is the training data. This is our distribution that we get here, which is our posterior. This is the same here. This posterior is this part here, right? It's the distribution over parameters given the training data, right? Once we have that, we can use that to kind of average out the parameters, right? So every parameter is just a possibility of a model, and we use that as a possibility to explain the test data, and that we simply do by multiplying with the likelihood here of the test data and then integrating out, right? This is the same idea as before, just have different kinds of possibilities of the model, and then we average them over all possible models, right? And in the training step, we do the posterior here. We compute this by Bayes rule. We say we turn things around, right? This is the kind of cause. And we take this in the opposite way. We say we take a cause and effect. We turn this around and say, let's compute the likelihood first and then multiply by the prior. Likelihood is simply the model that we do, right? Training data X and output Y. And this is what the neural network gives us. Question is how to compute those here, and I'll show you that in the next couple of slides. Before that, I tell you something about overconfidence, and I told you that, I think, in the beginning already. Overconfidence is a big issue with neural networks. You think of this as the following thing here. You have a function f, which is your network, that gives an output, right, for a given input x or x star. And that output is actually twofold, right? You have a label y or y star, and you have a confidence c star, right? And ideally, you have the result that the probability that your label is correct, given that the confidence is the right one, this probability should be equal to the ground truth confidence, right? Confidence is a value between 0 and 1. And intuitively, you want to have the probability of being correct equal to the estimated confidence, right? So if the network tells you I'm 80% confident that this is correct, then on average, you want the network to be 80% correct, right? Because then it's calibrated, right? It can tell you how confident, how correct it is. It knows that it knows, and it knows that it doesn't know. Of course, ideally, this is not always the case, but you can measure that. You can measure that by using these histograms here. These histograms, they simply count for every confidence value, how often has the network been correct or not. So for example, in this case here, you have this LeNet, which is a smaller and earlier deep network. Interestingly, the smaller networks tend to be less overconfident than the big ones. So the larger the network is, the more it tends to be overconfident. And you can see this in this histogram here. So for example, if you take the bin 0.6, that means you only count those samples that the network said I was 60% confident. Now, on average, ideally, all those samples should be 60% of the cases correct, right? Because then you have calibration, right? Then you have the exact same number of correct predictions as the confidence told you, right? Is that kind of clear? These are all things here. Let's say you have, I don't know, 10 examples where the network told you 60% confidence. In those 10 examples, you want to have 6 of them correct and 4 incorrect, because then you would definitely have the direct mapping between confidence and accuracy. In this case, it's opposite, right? So you have maybe of these 10 samples that you get, there's fewer are correct. However, the network tells you it's 60% correct, right? And that's the overconfidence. It tells you it's more confident than it should be. And that you can measure with this so-called expected calibration error, right? You just measure the expectation between the distance between these two, that is this P minus C. And if you take the expectation over some data set, then you get this so-called ECE. So yeah, so now the question is, and that's the next thing I'd like to show you is, once we have this network here, how can we compute good model uncertainty from these networks? And there's a number of things, a number of steps that you can do. I just mentioned all of these here, and I'm going now quickly through them step by step because they're kind of important, known methods to compute uncertainty from neural networks. The first one is a very simple one. The first two are actually quite simple. Then Laplace approximation is a more involved thing, and then the last two things are also quite short. So let's start with the first one. The simplest idea you can do is you take this last layer, the softmax layer, right, and compute the so-called entropy, right? The entropy is defined by this one here. It's the negative sum of pk times log pk, and pk is your probability that you get from that you compute with this one here, right? So the softmax layer computes here a probability for every class. K is a class, right, from 1 to n, or from 1 to k. So for every object class, you have this probability here, and that you're going to stick in here, and then use that kind of entropy value as a primer or as an approximation for the uncertainty. And intuitively, it means if the entropy is large, then the uncertainty is also large, right? Kind of, and this works quite okay, I would say. It's a very simple technique. It can be done for every network that is already has a classification output. However, this is exactly where the confidence comes from. So these plots here, they have been computed with that technique, right? So if you now use this method here to compute uncertainty, then you get overconfidence, right? This is exactly the problem. And the reason is that it doesn't take too much model uncertainty into account, right? The model itself, which means the network, that doesn't change. You always have just one set of weights here, and these are always the same in each of these summands here. So if you sum this up, you don't change the weights, and that means you don't take into account the different kind of model that you have, right? And for that reason, you have overconfidence. The next idea is this one here, which is already a better idea. And there you already have this idea of averaging. Here you do Monte Carlo dropout, and that's a very simple thing. You can simply cut some of these connections, which simply means that you set the weights to 0, right? So after training, once you have the training step done, you have these W's here, and you can simply randomly set half of them to 0, right? You say, I don't care what their weight is, I set them to 0. And you do this randomly, right? You do first these, and then these, and then these, and you do this a couple of times, right? And every time you do that, you do inference with your input, right? So after training, you look at the image, run through the inference, and set different weights to 0, right? That means this Monte Carlo dropout, which is usually done in training, can be done also in inference, right? During the inference step, after training, you just do this a couple of times, and that means you don't get just one prediction, but you get many predictions for the same image, right? You have the same banana here, and you get several different outputs, right? You say this could be, and then the outputs might be different, right? There might be one thing saying banana, the other thing might be saying apple, but on average, you hope that there are more kind of bananas outputs than apple outputs, right? But that's one thing. The other thing is you can average them, and by averaging, you can get an uncertainty, right? You can get the mean and the variance of these samples here, and this variance can tell you the uncertainty. And this works quite much better because now you have taken into account different kind of models, right? Not just one model, but kind of a bunch of different models. It still turns out, it tends to be overconfident, but much less than the predictive entropy as before. Okay, so use then statistic values. You can then take the mean and variance over these samples. Usually what you do is you take about 10, right? Question, yeah?
Is this affected when we swap out during training of the model?
So the dropout in training is done to do regularization. So so this doesn't affect the training at all, right? So it's anyhow done in training so often, and in the training step, it's done anyhow. But the key idea is, and that's kind of interesting, that people try to do that also in inference step without actually having big of a theoretical notion behind it. That just did it and said, hey, let's do this also in the inference step, and it worked. And then later they discovered what is actually done, so you can also prove that it actually works and it has certain explanations. But in the end, it's only effective if you do it in an inference step, not in the training step. Its training step is only for regularization, for getting better training, but not for getting better uncertainty. Okay, does it answer the question?
Not exactly.
Okay.
So if you do dropout during training,
yeah,
and your model gets more robust,
yeah.
So does this robustness affect this method?
No.
Okay.
No, it wouldn't.
Okay.
No. Yeah. That's a good point, actually. Yeah, the robustness is more for getting better accuracy, but not better uncertainty. Okay, the next approach I'd like to show you is Laplace approximation. And here the idea is the following. Let's think of these weights here, right, as a long vector, right? You just stack all these weights into a long vector. That means you kind of represent your function here in a high-dimensional space, right? And the result that you get after training is one of these vectors in this high-dimensional space. But how now, instead of just using one of these vectors in this high-dimensional space, I treat this as a sample from some Gaussian distribution in this n-dimensional space. And that means I not only have a mean vector, but also covariance matrix, right? And this we can then use to estimate the uncertainty. So what this means actually is, intuitively, is you have this log likelihood function, right? Which is done in the training step. In the training step, you maximize log likelihood. And of course, we know that these maximum are local, right? You don't have a global maximum, but assume that we have this kind of output after training, right? This mu w here is your parameter set that's the best set of parameters that you get from the training data. Now, instead of just using that mu here, what you can do is you can fit a Gaussian into the likelihood kind of landscape and interpret the resulting covariance matrix as an uncertainty, right? So intuitively, for example, if the log likelihood here is very peaky, right? There's a lot of there's a very high peak and then it falls down very quickly, then intuitively the uncertainty is lower, right? Because your covariance matrix is narrow, right? It's much more narrow than if the point here that you have is more flat, right? If you have a flat area, this maximum is more flat, then the uncertainty is higher because the covariance matrix that you fit in here would be kind of larger, right? And this is the intuition behind it. So a very peaked maximum gives you a more precise estimation of these models because changing a little bit drops very much more quickly the log likelihood than if it was flatter, right? So if in a flatter area, a small change in the parameters affects less than in an area where we have a peaked, and this is the intuition behind it. So basically what you do is you estimate the curvature of the log likelihood function, and that curvature is nothing else than a second derivative, and this is called the Hessian matrix, right? The Hessian matrix is nothing else than the second derivative at the position of your maximum, and you do the inverse of that, right? You invert the Hessian matrix to get the uncertainty matrix, or the covariance matrix here. And this we call the so-called Bayesian neural network. So very quickly, some math on that tells you why this is the case, why we do this, and what the reason behind that is. So we use Taylor approximation here in the log space. That means this is again the logarithm of our posterior. This is again the training step, right? So imagine we're in the training step, we want to compute the posterior here. We do this in log space for numerical reasons. So we can estimate or can approximate that log posterior with the log of the posterior at the maximum. That is W hat is the maximum here, right? So this is where is it? It's here. This is W hat, right? Or mu W, which is the same here in case, but this W hat is this maximum here. Then we have a linear term which vanishes, right? The linear term in Taylor is vanishing because we are at the maximum, and that means the first derivative is 0 by definition because we are at the maximum. And that means we have only a second order term, right? The second order term is this Hessian matrix times W minus W hat transpose, and that multiply from both sides. But this is the second order term of the Taylor series approximation, and we can compute that by deriving the log likelihood and log posterior twice, right? So it's a double derivative, right? Which is nothing else than the so-called Hessian matrix. Here we can then apply the Bayes rule, and now we see it might look like different right now, but it's exactly the same thing. This is Bayes rule in log space, right? Instead of multiplying things, we sum up things, right? Log of posterior is equal to log of likelihood times log of prior, and in log space, sorry, in log space it's a sum, right? This here is a sum because we're doing logs. But other than that, we just have the same thing as before, right? This is the likelihood, this is the prior, and we just sum them up. And intuitively, we have actually two matrices, right? A log likelihood matrix and a prior matrix. Then what we can do is, once we have this approximation, we can take the exponential on both sides, right? We can say, let's take exponential, get rid of the log. That means we have this kind of formulation here, right? And now we look at this already quite like a Gaussian, right? This looks pretty much like a Gaussian. It's not exactly a Gaussian because we have this issue with the normalizer here. That means we have to normalize it, right? We have some function here that says, okay, P of W should be roughly a Gaussian here. That means we have to make sure that, the normalizer of the Gaussian is correct. That means we have to divide this by this normalizer here to get correct Gaussian. The essence of that is, in the end, we estimate that posterior with a Gaussian distribution, right? And that Gaussian distribution has a covariance matrix that is equal to the inverse of the Hessian, right? That's the whole point of it. So that means we have to compute the Hessian matrix, right? Which is the big art of that. How do you compute the Hessian matrix? And then once we have that, we can do predictions. And this is again the same as before. We have the predictive distribution here, Y star given training data and X star. And then we do this marginalization step where we marginalize out the W's. And this is now easy because this is a Gaussian and this is a Gaussian. But we can do this in closed form if these are Gaussians, or if not, what is also actually very often done is we approximate them with a sum, and this is called Monte Carlo integration, right? We sample from this Gaussian here, from this posterior Gaussian, and every sample will then be sticked into the likelihood, and then we sum this up, right? So this is the usual idea how to do that, right? This is the inference step. Once we've done the training, we use those training samples to do marginalization in the inference step. Okay, and this is just an example how this might look like. So the posterior is something like this one here, which is a multimodal distribution. This is this blue curve. And what we do now is we kind of fit a Gaussian into the maximum, right? So this is the maximum of the blue curve. And at that maximum, we fit the Gaussian, which is this red curve here. Now, the big question is how to compute this H matrix, because this H matrix is very inefficient, right? You can imagine if this network is very large, then you have thousands or hundreds of thousands of parameters. And that means this matrix here is 100,000 by 100,000 or even more. And to invert that kind of matrix is infeasible, right? You cannot just run your invert function on that. And there's all kinds of ideas how to do that. The first one is the following. Let's do the following thing here. We say this is again our Taylor approximation. We do the second derivative of that, right? And I think this is just a repetition of before. That means in the end, what I do is I have this sum of log likelihood and log prior, right? And I think this is just a repetition of before, right? Yeah, sorry for that. I just mentioned that already. It's good to see this again. So what we do is we take exponentials here on both sides, and then come up with this unnormalized Gaussian here. So this is some kind of technical details how we can do this. We call these matrices the so-called GNN matrix, the generalized Gauss-Newton matrix, which is equivalent to this Hessian if we have piecewise linear activation functions. For example, if in a network uses ReLU functions or ReLU activation functions, then we can apply this here and can say the Hessian is equal to the generalized Gauss-Newton matrix. And that again is equivalent to the Fisher information matrix when the loss function is from the exponential family, for example, if we have a squared error or cross-entropy loss. These are technical details which are not too important right now. The result of that is what we can do is instead of using the Hessian, we can use the so-called Fisher information matrix. And that's much easier to compute than the second derivative. In fact, it's only the first derivative, and it's taking the outer product of that, right? So this delta theta is basically the gradient of the network, which is just a derivative in all parameters as a big vector. And if you take that vector with itself, right, multiplied with itself in an outer product, you get a matrix. And this is kind of the definition. So this delta theta is again our gradient, which is the Nabel operator on the posterior. Or this is actually the likelihood, but you could also do the posterior, of course. And that gives you then the Fisher information matrix, right, which is easier to compute. However, it's still very, very expensive because we have this very large matrix. The next step that you do is you assume that across the layers, things are uncorrelated, right? So one weight doesn't influence the other weight in a different layer, right? So these matrices now correspond each to a different layer in the network, right? And now we have, of course, a much better representation, a much easier representation, because we have to invert only these block matrices here and not the whole matrix, right? Of course, it's a strong assumption maybe, but it works in practice because very often these weights that are across different layers, they are not very large. So there's not too much correlation between them, and that means you can kind of safely assume that these are zero, right? And that means you just continue with this set of block matrices, right? Which are now much smaller, right? Now, each block of these, again, we can look at them even closer and can say how they look like. The interesting thing here is, because they come from the neural network, you can write this down in this kind of Kronecker product here, right? This operation here is a Kronecker product where you take one matrix and pad it with the other one, right? You just multiply one matrix with the first value of that matrix and then do this across the entries of the other matrix, right? So the result of the product is then a matrix that is as large as this one times this one squared, right? So let's say this is n by n and this is m by m, then the result is n times m by n times m, right? You just pad one matrix with the other one. It's like tiling the matrices with the other one. And you can show that this is actually possible because the network has this kind of structure, right? So we come from both sides, from the gradient from the right side, and from the h from the this is the pre-activation h here. In the end, it's nice to see this, right? Because it's because the network is structured in that way. In the end, you have these kind of two outer products, this h times h transpose, and the other one, this one here. And each of them, and those two together can be multiplied with this Kronecker factorization. And now comes the last step, and this is kind of an important, again, approximation step. If you now approximate this product with the product of the individual expectation values, right? So you now take expectation of h times expectation of g, then you can write this in the factor in this kind of way, right? You can say this is a and this is g, and all you do is this kind of Kronecker factorization in this low-dimensional space. So to get this a bit more in detail, what you can now do is you can then decompose these matrices because they're positive definite and symmetric, right? You can show that this is the case, and that means you can decompose them. You can compute their eigenvalues and eigenvectors, and you can do the same also for A and G as well, right? So A and G themselves can be decomposed into their eigenvectors and eigenvalues, and now you use this nice property of the Kronecker factor that these kind of distribute, right? So you say A times G is this decomposition times this decomposition. And now you can distribute the Kronecker factor or product over the matrices, right? You can say this is the same as UA times or Kronecker times UG and this and so on, right? And this is nice because you never have to compute actually the big matrix, right? You never have to compute A times G, right? You always work in this kind of low dimensional space where we have UA times UJ, G, and SA times SJ and so on, right? This again is a diagonal matrix. That's also a nice property. If you have two diagonal matrices and you Kronecker factor them, then you get another diagonal matrix. And the same is also true here, right? So this matrix times this matrix, they are all rotation matrices or orthogonal matrices, and the Kronecker of them should be also an orthogonal matrix, right? So this is the kind of nice property of that to make things more easy to compute. And in the end, you have two kinds of matrices. One is V and one is lambda, right? By simply setting this equal again to that one here, that means this V should be this left-hand part, and this lambda is this center part, right? Of course, all approximated. This is the approximator here, right? So this lambda is approximately this here. And from that, you can then compute an approximation of the eigenvectors and eigenvalues, right? You can then say lambda is the expected value of V times of this output, right? So you take this V transpose, and then multiply it back to F, right? To kind of solve this equation for lambda by simply, multiplying from left and from right with V transpose and V, right? To get on the left-hand side, and that means you have this operation here, right? In the end, you just have an outer product of transposed gradient vectors, right? This delta theta is a gradient vector which is transformed by V, right? And then it's multiplied by itself, and that gives you the this lambda here. So in the end, you have a kind of nice way of computing these lambda values, and they are now more approximate. And now the F matrix can be approximated with these lambda values, right? These are then, and you can show that these lambda values are better, or more approximate than the original ones that you do if you just do where is it? If you just do this, sorry, here. Yeah, if you just do this one here, right? So instead of doing that, you can compute these lambda values with this approximation here and get better estimation of the Fisher matrix. Okay. Okay, I think this is that slide. Sorry for jumping. So again, this is our new approximation. F has now the rotation matrix UA times UG times lambda times UA times UG, right? This is your new F matrix, which you can then use to compute the uncertainty, right? And another interesting thing is one important operation, and this is what we had at the beginning, is we have to invert that matrix, right? Remember, inverting that was difficult. Yeah, question?
Or is it's too expensive?
No, it's not expensive. These matrices are rotation matrices. These are orthogonal matrices. And the thing is, you don't have to ever compute that because you have to only invert that matrix. And inverting that is possible on the level of matrices. This is, I think, true. Yeah. So there is a so in the end, what we do is it's a Gaussian with that covariance matrix. And there's a formulation of the Gaussian where you don't have to ever compute UA times UG, right? All you do is inverting lambda and inverting these individual matrices as well. And that's it, right? So then you have this F inversion. You don't have to compute this from here. Yeah, that's a good question. Thank you. Okay, now once you've done that, this is again the training step, right? Remember, we have applied now base rule. We have computed posterior. This is this one here. And now we do predictions by doing marginalization, right? We average over all possible models, and we do this again using Monte Carlo integration, right? So we sample from this Gaussian here, right? We have a Gaussian distribution over parameters, right? And all we do is we sample from that posterior, which is easy to do from a Gaussian, right? Sample, for example, 10 or 15 samples here, and in the end, and each of them gives us a prediction. right? We then stick the W into the network, do a prediction with the network, and then have some output which we can then average and then also find the uncertainty from that, right? So this is basically the major idea of that. And we do this by inversion of this F measure. So F basically sits here because we approximate sigma by F inverse. That means we inverse F, sit it in here, sample from that Gaussian, and get output here. This is an example of how this slide might look like. We can use that method to find the out-of-distribution samples. And that means what we can do is we can train the network with some kind of data, like this one here, and show it different data, right? So this data here is, for example, images of real images of animals, like this one here, the hamster, and all these kind of things. And the test data is different. It's artistic impressions, paintings, right? It looks definitely different from the training data. And the question was, can the network detect that? Can the network see that there's something different in the test data than from the input data, right? And if you compare that with different methods here from the past, if you just do deterministic runnings, right? If you just ask your network directly and don't do any Bayesian operations, then you see that the OOD data, right, which is this test data, overlaps quite a lot with the training data, right? If you show the network known images, then the entropy, now again, we use this entropy as an uncertainty, right? Kind of doesn't distinguish between the known and the unknown things. However, with this one here, we can use the entropy, right, as a separator between the unknown and the known things, right? Now the entropy is more informed, right? It gives you a better indication of something that is known or unknown, right? Now we can threshold it and say here, if the entropy is larger than a certain value, then we are in the unknown space. And if it's lower than that, we are in the known space, right? We can separate the known from the unknown easier with the entropy. Okay, so far the topic on Laplace approximation. This is, as I said, one of the big things how we can do that. And then there's the final, another thing which is also quite an interesting approach and a very simple approach, which is called ensemble methods. And there's actually two ways of doing that. One is bagging, one is boosting. Bagging is kind of an old method which is not used so far anymore. So here we have many different classifiers or many different networks that work in parallel. And sorry, boosting is the older one, bagging is the current one. So the idea here is and it's the same idea as before. You sample different models, right? And then query them all at the same time. And then in the end, you take some average over them, right? So to actually also get model uncertainty. Boosting, what you do is you do this in linear space. You just take one model and then train it on some data and then use this next model that is trained on the output of that one and so on. So there's a linear or like a sequential connection between the models. In the end, you also take an average over all them, right? Here you see the effect of that, right? So what you want is a low bias and a low variance, right? So bias and variance trade-off is also known in machine learning as a big problem. So if you have high variance, you can think of this as hitting at the same goal, but many of these models that you use are spread around the main goal, right? So the average of them is correct, right? If you just take the average of them, that's correct. But many of them actually are incorrect because they're far away from the center. And if you have a high bias, this is the problem of usually I think of bagging methods. Then many models kind of agree, but they are far from the ground truth, right? This is the opposite case. And what you want is both. And with bagging, you can actually mitigate that problem and get both low bias and low variance. Now we apply this now to deep learning, and this is the idea here. What we can do is now we can generate different networks, right? And each of those networks just gives a different output, right? And in the end, you take averages here, right? You say the output mean, for example, you take the mean of the output, you take the variance of the output, and these are then indicators of your uncertainty, which is a much simpler technique than before, right? You don't have to do any approximations, you don't have to run any Laplace approximation and so on. However, it has this big disadvantage that you have to store all these methods, all these things, right? So deep ensembles are very memory expensive because each of these networks has to be stored in memory, right? And if you take 10 or 20 deep networks, then very often this gets inefficient, and it's also like a time issue, right? So you really have to query them all and so on. But they work quite nicely, right? So if you want to good uncertainty methods, then deep ensembles are a very good method to do. Okay, and the last thing I'd like to show here in terms of uncertainty estimation is classifier calibration. This only works when you do classification, right? So not in regression. So again, we have this output here where the output gives a probability of a class label, right? So this could be class ABC, and every class has a probability. And the idea here is to make sure that the output here is calibrated, right? And that we can do with an additional training step, right? So ideally, what you do is you take some holdout data set from the training data and then fix the previous layer, right? So kind of adjust the previous layer that goes into the softmax layer. And this fast or second last layer, we call this the logits. These are the numbers here, Z, that go into the softmax layer, right? And this is basically this function that is learned. It's a so-called calibration function, right? These are the logits here. And for each of these logits, you get an output, which you then stick into the softmax layer, right? To kind of deviate the curve, you say, put these outputs into the calibration function and the output of the calibration function into the softmax layer. And you do this such that the output of that is calibrated, right? That means you have a ground truth of your labels, and you kind of fix that so that your calibration error goes down, right? You kind of minimize the calibration error by, or find a smaller calibration error by fixing this calibration function, okay? And there's a number of ways of doing that. First of all, the advantages of that is it can be applied to any kind of classification function, right? It doesn't matter which technique you have here. You only apply this to the last two layers. It's independent of the loss function, right? You just do this after training. Once the network is trained, you can apply it. And it's usually easier and faster than training several models or using Laplace, right? It's a straightforward way of doing that. It's kind of fixing or modifying the network. It has also some drawbacks. It requires some additional training data set, which we call the calibration data set. But usually this calibration data set is smaller. You don't have to have a big training data set here. And it needs a defined calibration function, right? You have to define this function and you have the way of doing that. What we can also do is we can use a so-called non-parametric representation, and that we can do using a Gaussian process, right? Gaussian processes are known to do very good regression. And basically what we have here is a regression problem, right? We have to find a mapping from logits to the softmax layer. And that's nothing else than a regression problem. And we can do this with a Gaussian process, which I'm not covering here. I think this is something that is covered in other lectures. It's very simple, just a non-parametric representation where you just have samples, right? And you kind of do a weighted average basically on those samples to do the regression. So basically this is shown here. So we have this VK, which is the sigmoid of these G functions, and G is now the function that we learn. G is our calibration function, and we apply the G to all the Z inputs, Z1 to ZK, right? And the probability is then just the product of these VKs, right? The details of that I'm going to skip here. I'm just showing the results of that and how this might look like. This is a result of like a whole bunch of many different network data sets and networks, right? These are networks here, these are data sets. And these are the numbers that give us how well is the network calibrated, right? So this is the ECE, right, which I showed you before, right? The expected calibration error. And this should be as small as possible to show that it's not overconfident. So if ECE is small or 0, then the network is not overconfident. And we can show with this method here, with the GP calib, most of these networks and data sets actually reduce the overconfidence. That means the network, the ECE goes down because we have a better way of estimating this calibration function, right? So you can show in general it's the best method for the first one here, right? For this AdaBoost method, it's the first one. And AdaBoost actually is not a network, right? It's a different classifier, right? You can apply this to any classifier. It doesn't have to be a network. It can be any classifier that you'd apply. It's also significantly better than others, except this AlexNet here, and it outperforms others for 9 out of 13 architectures, right? It's quite a strong thing here. And it's also important that it doesn't worsen the calibration, right? So it's before and after it cannot be worse than that. Okay, now let's summarize that a little bit and go kind of towards the end of this lecture here. I've shown you a whole bunch of different methods to do uncertainty estimation. And I'd like to show you in the last couple of slides what you can do with this, right? So why is it useful to have this uncertainty? And yeah, as I've said in the beginning, it's very often important that you distinguish between known and unknown objects or things in the environment. And I show this here in this little kind of flow chart, right? If you have a manipulation task, then the first question that you do is, are all the objects that you have to manipulate known, right? Is everything that you see in the environment known already? And if that's yes, then you can use this kind of standard pipeline. You know all the objects, you do object detection, object pose estimation, graph detection, and so on. And you find this here, right? You can just assume that you know the cup, you know all the other objects in the background, and so on. However, and that's what I said at the beginning, usually we don't have this situation, right? Very often we have these unknown things in the background, right? We don't know what the keyword is. We have no model of cables, for example. This is another big issue, right? How do we model cables and so on? So this in general doesn't work, right? Because very often, yeah, we just have enough other objects that we cannot reason on, and we call this object blindness, right? There's something we don't know yet. It could be either clutter, which we don't want to collide with, or it could be other objects that we'd like to interact with, and we have to know that. This is the classical pipeline: detection, pose estimation, graph detection, and so on, and we do this here. Now, the opposite case is also interesting, and it's more difficult, but also not too difficult. If everything is unknown, right, then it's also easy because we can treat everything the same way. We can say, I don't care what this is. I don't know what its name is, how its semantic is. I just need to find a geometric way of interacting with it, right? So let's say there's a bunch of objects on the table, and I'd like to grasp them. If I don't care what they are, I just find a geometric representation, a point cloud, a mesh, whatever, and then kind of learn how to grasp that, right? And then find a good path to do that into the grasping. And I don't have to distinguish known from the unknown because everything is unknown, right? It's then kind of easier. It's not as easy as the other one, but it's also comparably easy, right? So if yes, then everything is unknown, which makes it easy, but then I have to decide whether I need to do something with it, right? If it's a useful grasp, right? For example, I need to use that tool, then I have to grasp it this way and not this way because I cannot use it this way, right? It's a functional grasp means I need to know how to use that object. If I don't care, I just want to place it somewhere else, then I don't care where to grasp it, right? Because I just pick it and place it, and it doesn't matter where to do that, right? However, if I have a functional grasp, then I have to do some reasoning and have to find better finger positions. So this is this one here, right? If I don't care, I can just do a direct grasp detection. And this is this example here, right? So we have, we call this contact grasp net. This is also applying some deep learning here. Right? We have deep learning to do the graph detection, and we have deep learning to do the segmentation. And we do this simultaneously, right? We have a segmentation method that simply finds from a stereo image the contours of the objects without knowing what they are, right? Simply finds the contours. You see the stereo camera here. This is the stereo camera, which looks at the scene. We also see the projector. With this projector, you get a dense point cloud, right? You have this projection, and then you have more correspondences between the pixels, right? You can then compute a denser point cloud by looking at the correspondence between the two images. And then from then you get these kind of segmentations here, right? And the interesting thing is now is you can just tell the robot to grasp whatever it sees and pick it and place it away, right? So this is what's done here, right? And even if objects are overlaid and stacked and so on, it finds the grasp, right, in this scene here in the lower left, and moves it away, and then does another segmentation round. And as soon as it's done, right, if there's no segmentation anymore, then it's ready. However, this works only if you can assume that everything is unknown, right? If you don't need to distinguish between the known and the unknown ones. The second branch here is this one here. This is this functional grasping yes. So there you need to do something with the object, right? And that means you have to do other things. For example, the bottle here, if you want to grasp the bottle, then you need to kind of look or see how that looks like from the other side, because otherwise you wouldn't be able to use it, right? So this is now a robot that has more fingers, of course, and those fingers can be used to do some useful things with the objects, right? So pour some water from a bottle, use a cereal box like this one here. And this is done now with techniques where we do completion of objects, right? You do a 3D completion of the objects and then find the correct positions of the fingers. And finally, and this is the interesting thing right now for this kind of application for the lecture here, if there are objects that are known and unknown, then you can use the technique now to decide whether something's unknown or not, and then treat those differently, right? And we call this introspection. I think that the last couple of slides show a more recent idea of combining learning with reasoning. This is kind of very quickly, I'm not going too much into detail because of time, but I'm just telling you that there's a kind of nice idea to do that, where you can combine the properties or the power of a Gaussian process with the properties of a deep neural network, right? So deep neural networks and Gaussian processes, they are related. There's a theorem that says that a Gaussian process is basically nothing else than a deep neural network that has a width of the layer that goes to infinity, right? So the wider the networks are, the more they look like a Gaussian process, right? And with that idea, you can actually say, oh, let's use neural networks to get uncertainty and combine them with a Gaussian process, right? And this is one idea of doing that. They provide the so-called neural tangent kernel. I mean, you might have heard, if you talk about Gaussian processes, you have to define a kernel. And the idea here is to use the neural network to define a kernel, right, which is then stick into the Gaussian process. So here, there's these 3 steps here. You approximate the posterior. This is the Laplace that we did just before, right? This is the same idea as before. You compute this posterior with the Laplace. Then you find this linear model here, y tilde, so that its posterior equals the found Gaussian approximation. And this is the result of that paper here. It's easy to do that by looking at the Jacobian. This is the derivative of the network with respect to all parameters, right, at the training step, right? So after training, you derive the network with all the parameters, which you already have, right? This might be a vector, but it could be also a matrix, because if the network has multiple outputs, then this is a matrix of that many outputs derived by all the parameters, W, right? This is a matrix then. And the fun thing here is you can use that as a kernel, right? You can use that as a function that is multiplied by itself, and that kernel can be used to compute similarities between data samples, right? So if you have 2 data samples, X and X prime, then the similarity, which is what the kernel says, can be computed with these products of these Jacobians. And this we call the so-called neural tangent kernel, right? And that kernel can be used as a Gaussian process in the Gaussian process to get uncertainty, right? So we've basically, the Gaussian process gives you the uncertainty. This is the sigma here, right? And the network gives you the output, right? The network tells you label A, B, C, right? This could be, I don't know, class, banana, apple, whatever. This is what the network tells you. And the GP tells us the uncertainty by sticking that neural tangent kernel into the GP. Of course, the details are a bit more involved because the GP is very expensive. You cannot do this that easily. That means you have to do some kind of subdivision of the space. Here, what we do is we do a subset of experts. That means instead of having one GP, we have kind of a mixture of GPs, right? Each of these GPs has a certain sub area of the data space, which makes it more easy to handle, and so on. So there are a lot of tricks you have to play because it's quite expensive to do that. But the main idea is to kind of use the GP, power of the GP, together with the neural networks. And this is the result here. The good thing about this is it's small, it's nice and small, and you can run this on a drone, right? So you can have a drone here that flies around, right? So you have two classes that you want to detect. One is this space lander. It's kind of hard to see in these images, but sorry for that. These images are not so good quality. So it's basically the drone flies around and sees two different things. One is the space lander, and one is this the space rover, right? So these are two classes that you want to detect. And the problem is you have these kind of out of distribution samples here where other things are in the background and you might not be able to detect that well. And what we want is we want to have a high uncertainty on those here because they are very likely to be wrong, right? If you have some samples here and here also as well, right? So this looks much different from this one here. And if I have a prediction on this sample, I would like to have a higher uncertainty. And I think the video should be able to show that. If you take the regular uncertainty here, I think it's very hard to see. I'm sorry for that. Then you will have the bounding box of that, and you get the label, but you get low uncertainty on the wrong detections. And in this case here, you just do the opposite. You see, even if it's wrong, right? This is called lander right now, which is of course wrong, but it has a very high uncertainty or low confidence, and with that you can distinguish unknown things from the known things. You can then separate them and say, if the uncertainty is too low, then I don't trust this and say this is a wrong detection. Okay, with that, I'm already at the end of the presentation. I'd like to conclude this lecture here today. First of all, I hope I could tell you something about introspection and what introspection actually means. It's the ability of a learning method to predict its failure probability, right? So it knows when things are known and it knows when things are unknown, right? It can distinguish between one and the other. And this works both for regression and classification. We've seen that neural networks, and this is of course the standard method of today, in general, they tend to be overconfident, right? That means they usually make wrong predictions with high confidence, right? They do very few wrong predictions. That's true, right? Neural networks are very good at estimating labels and doing some predictions. And you might argue, well, it's not a big problem because if they are 99% of the cases correct, then why would I care about the 1% of the cases where they're wrong? Well, in robotics, this is a problem, right? You don't want to have this one case in thousands or hundreds of thousands where it's wrong, but it's wrong and certain, right? This is what you want to avoid, right? So you could think that maybe sometimes it's better to have a network that gives a less accuracy, right? Maybe only 95%, but at least in the 5% where it's incorrect, it's uncertain, right? So at least it can tell you, well, this might be wrong, right? And you might do something with it, instead of just being convinced that something is correct, because then humans cannot mitigate it, right? They cannot interact, they cannot do something with it. They have to trust the system and say this should be correct. Then I showed you at least these 5 methods to get uncertainty from a neural network. That's Monte Carlo dropout, Bayesian neural networks with Laplace approximation. This is what I showed you here in more detail. Then I showed you deep ensembles and some about classifier calibration. In the end, I showed you the sampling free method only very shortly. This is quite a promising thing because you don't have to run several samples through the network, right? You have a nice way of combining Gaussian processes with neural networks in this NTK method. And it's quite a promising thing. It's not that easy to implement because there's some details yet, but I think this is quite a nice idea. Yeah, and we can use that to distinguish known from unknown objects. I've shown you some examples how to do that with this drone flying around to detect these 2 objects. Yeah, so this is basically this OOD samples, right? So out of distribution data that can be detected with these methods. And finally, introspection only gives a hint, right? Again, this is a lecture on explainable AI. It's not there yet, so we're not explaining why things are wrong, but at least we can detect them and can tell us that things might be wrong, and then do the next step and find reasons for those being incorrect or not. And with that, I thank you for the attention. Yeah, questions?
For classifier calibration.
Yeah.
Another lecture, there was said that networks with softmax activation, they tend to go for top 1 classifications, so they feel more certain than they truly are because they try to optimize for one prediction.
Yeah.
Is this counted for? Like, does this approach, is it less good than others?
No, I think this is exactly the thing. I think this explains exactly what this means. So what, if I get correct, what you say is that classifiers tend to have one class very likely and all the others less likely. And this is not equal to the true probability of that class, right? And this is exactly what we mean by overconfidence. So they tend to be overconfident. They tend to have one class that are very strongly voting for and telling this is 80% sure that this is this class. In fact, if you look at its statistics, it's less often correct. And it should be more humble. It should be more saying, oh, I might not know this. And calibration does exactly that. So calibration fixes that, right? And reduces that 80% to 60%, right?
In the last approach, was a mixture of the daughters. You might divide the space into more areas that you actually need to.
Yeah.
If you have continuous clusters.
Right.
Have there been approaches that tackle this in some way?
No, not yet. That's a good point. If you do this here, this subdivision into spaces, then of course the question is always, and this is whenever I see mixture of, I ask the first, how many mixtures do you have? Right? This is the first question. How do you decide this m function, m number? And it's in the end, it's empirics, right? You just try a good number and it works for your data, and that's it. And of course, in this case, what we do is we have overlaps, right? We don't have clear separation between those because some samples might be here and there. So that's also a thing to deal with. Yeah, in the end, this is the classical problem of mixtures. And there are techniques to do that. I think in general cases, there are techniques. For this particular case, we didn't do this. No. Yeah.
When you choose a certain type of distribution, say, for example, Gaussian,
Yeah.
distribution, any kind of distribution, have there been approaches where you try to have a more general distribution, for example, approximated by splines?
Yes, there have been. So Gaussian processes can be shown to be a general case of splines when you use a certain kernel. So that's the nice thing about Gaussian processes. Gaussian processes are very general, and they're only defined by their kernel. So and this is the reason why they're kind of non-parametric, right? You don't stick to a certain model behind it. You only define what is similarity, right? What do you understand by A is similar to B? And that's the kernel. That's the only thing you stick into the Gaussian process. You're right in when you talk about Laplace approximation, then we apply Gaussians, right? We assume Gaussian distributions and so on. And the question is that correct or not? In fact, there are newer techniques right now, newer theories that also address more general distributions, right? So Gaussians very often are not sufficient. They're often used because they're easy to compute. That's a good reason, but probably not the perfect reason, because very often they might not fit, right? They might not be representing the true distribution behind it, right? So only because it's easy to compute, to multiply prior with likelihood shouldn't be the reason. But yeah, that's a good point. There are newer theories that put this all in a more general framework, right? Where we have a distribution at prior and another distribution at the likelihood, and then you just have to kind of multiply the two. And that works more general, but it's not yet done in practice.
Do you have a keyword for this?
No. If you send me an email, I can give you the keyword. I just saw a talk on that online just recently. I'll point you to that. Other questions? Then thank you very much.